Alrighty, so we're going to look at finite difference numerical methods. Okay, and we're going to first start with just the Taylor series. Approximations, so we can kind of see where all this comes from. And so with a Taylor series, if I look at a function and here's a function, and I say there's x, and, well, actually make that x minus h. We'll make that x, and that x plus h. Okay, so I can look at various things like this. Well, the idea of a tangent line, right, is if I know the tangent line here at x, I could draw that tangent line, use that to predict the function f at either x plus h or x minus h, something like that. I could use, instead of just a straight line approximation, I could use a quadratic approximation and so forth. So, let's look at this idea. So if I want to, say, approximate f of x plus h using a Taylor series, then that Taylor series at x, you expand it at x, would be f of x plus f prime of x times h, or delta x, plus f double prime of x, h squared over 2, plus f triple prime of x, h cubed over 3 factorial, and it would just keep going like that. Now, so the idea is that if I would like to, say, approximate the first derivative here at x, I could do that simply by using this approximation and cutting it off somewhere. But notice if I subtract f of x from both sides, I get f of x plus h minus f of x is equal to f prime of x times h plus f double prime of x, h squared over 2, plus f triple prime of x, h cubed over 3 factorial, and plus, and wherever I stop it, I stop it, but for now we can just say it keeps going. Now if I divide both sides by h, then you see that f of x plus h minus f of x over h is equal to f prime of x, and then plus some other things. So plus f double prime of x, h over 2, plus f triple prime of x, h squared over 3 factorial. And so what we see is that, what we would say is that f of x plus h minus f of x over h, that quantity, is approximately equal to f prime of x plus some error, okay? And that error is based on h, the size of my delta x. Now, because typically delta x is going to be less than 1, so if I take delta x squared, or h squared, that's, say h is a 10th, right? If h was 0.1, then h squared is clear down at 0.01. So, these terms become much, much smaller than this term. And the way we would talk about that error is we would say a big O of h. Okay, we've got some constant f double prime of x times h is our main term. So we call that big O of h for our error. Okay, so our error has to do with how big our delta x is. Okay, so if we, draw our picture, here's x plus h, then what we're saying, let me curve that a little bit more just so we can really see better. So there's our f of x, there's our f of x plus h, and what we're doing is we're saying the slope here is pretty close to the slope there that is the actual slope. Okay, it's going to be off by a little bit on order of h. And so as we move this in closer, we can reduce our error by reducing h. Okay, but there's an approximation for the first derivative. Now, I could actually do it on the other side as well. Okay, so if I look at, whoops, come on. Oh, I don't know what just happened, but I'm not sure why I can't keep going. Usually I can scroll down. Oh, there. We got to do that. There we go. Okay, so if I instead wrote f of x minus h equals f of x. Now the difference is with the minus h, what we're doing is, as we look at these 2 points, here's x minus h, we're going this way, and so actually our delta x, or as we think of our h, that's actually going to be a negative number, okay, because we're starting here at x and we're taking, in the Taylor series, we're always doing this value minus that value. Okay, so that'll be x minus h minus x, that's a negative h. Okay, or in other words, we're less than 0 if we look at it that way. So so let me start that over. F of x minus h, f of x, but then minus f prime of x times h, plus, because we'll get an h squared, so, or minus h squared, so then f double prime of x over 2h squared, and then a minus f triple prime of x h cubed over 3 factorial, and it'll keep going on. Okay, so we have that. Now, if we do the same thing where we subtract the f of x from both sides, divide by h, we have our f of x minus h minus f of x over h is equal to the negative of f prime of x plus f double prime of x h over 2, and then minus the f triple prime of x h squared over 3 factorial and plus dot dot dot. Okay, so if we change the order here so we get negatives to disappear, right? If we say, well, f of x minus f of x minus h over h, that is also f prime of x plus, and I'll still use a plus even though we put a minus here, big O of h. So the error is still the same. Okay. So that, here I'm looking at my 2 points, but I'm looking at x and x minus h. I'm still trying to, not very good there, but trying to approximate the derivative here, but now I'm using this slope. And again, it's going to be close, but it's going to be off by a little bit. But as I make h smaller, I can make this approximation much better. Okay, so if we go back here, I would call this a right-hand approximation. Okay, because I'm moving to the right. Here, I would call this a left-hand approximation because I'm moving to the left to get my other point to try to get that slope. Okay, but now here's something novel. Let me write them both out again. So if I take f of x plus h, okay, that's my f of x plus f prime of x h plus f double prime of x h squared over 2, and I'll go to the f triple prime. We keep going, but I don't want to. Okay, so we have that, and then f of x minus h is f of x minus f prime of xh plus f double prime of x h squared over 2 minus f triple prime of x h cubed over 3, and of course it keeps going. Now notice though, if I take f of x plus h minus f of x minus h, in that case, those cancel when I subtract, and here I'll get 2 f prime of x h. Then those will cancel, and I'll get plus 2 f triple prime of x h cubed over, 3 factorial. And then plus some other stuff. Now, if I divide both sides by 2h, okay, 2h like that, then you see I get my f prime of x plus, and notice here I divide by h, so I'll get an h squared. The rest of the constant, well, the 2 will disappear, but it doesn't really matter. I'm going to call this big O of h squared. Okay, this is h squared, not h. Well, so if you think of this in terms of error, you see the error is much, much smaller. Because again, if h is 0.1, then back here with this right and left hand stuff, our error has something to do with 0.1. But here, our error has something to do with 0.1 squared, or 0.01. Okay, so 10 times better if h was 0.1. And so actually, and we call this a centered difference. And again, if you tend to look, if you try to use pictures as your inspiration, here's x minus h, here's x plus h, and if I want to get the slope here, it looks like in the picture that this slope here that's the slope we just found, looks much closer to that slope than if we took either the right or left-hand side. Okay, so intuitively, it looks like this center difference would do better, and it does. Okay, it actually, if you keep making H smaller, it gets a better approximation much faster. Okay, so we kind of like the center difference idea for this, but we'll kind of look at all three. So there's the first derivative. Okay, so we've found a way to approximate f prime at x. Okay, and we can either use a right hand, we could use a left hand, or we could use a centered difference. Okay, either of those is fine. All right. Now let's look at f double prime of x. Okay, so same idea. We've got f of x plus h equals f of x plus f prime of x h plus f double prime of x h squared over 2 plus f triple prime of x h cubed over 3 factorial. And I got a little room, so we'll go to f4, fourth derivative, h to the fourth over 4 factorial. And similarly, I could write f of x minus h, f of x minus f prime of x h plus f double prime of x h squared over 2 plus f triple prime of x h cubed over 3 factorial. Oops, that should have been a minus. It's a minus. And then a plus. F fourth derivative, 4 prime, h to the fourth over 4 factorial. Now, notice if I add these two. So we take f of x plus h plus f of x minus h. That equals, if I add them, I'll get 2f of x, but those will cancel. And then I will get plus f double prime of x h squared, because those are both over 2. And then the triple primes will cancel. And then I'll get plus 2 f fourth derivative of x h to the fourth over 4 factorial. So now, if I subtract the 2f of x from both sides and divide by h squared, I get f of x. Now I'm going to put these in a slightly different order. I'm going to do it as f of x minus h. So I go from left to right on the number line. Minus 2f of x plus f of x plus h divided by h squared equals, well, so I move this over, divided by the h squared, so I just get my f double prime of x, and then plus dividing by h squared here, I'll get an h squared, and so I'll just call this big O of h squared. So there, my error term is on the order of h squared. it'll have, you know, an h to the fourth and an h to the sixth. But again, if h is small, then h squared is much bigger than h to the fourth or h to the sixth or something like that. So we use this for our error term. So here is a second derivative. And again, you know, if I'm trying to look at the concavity of something, you know, here's x minus h, there's x plus h, you know, here's f at each of those. And this says if I take this f minus 2 of that one, and then plus 1 of those, divide by h squared, I get a pretty good approximation of the second derivative, f double prime of x. Okay, so those are our approximations using Taylor series. Now notice this is kind of a centered sort of thing here. You know, it's symmetric on each side. Okay, but I have a first derivative and a second derivative approximation. So we'll stop this video here, and then we'll look at applying these to a partial differential equation.